This is CPE 233, one of the first lectures here. This is going to be essentially a review of digital design, which is, of course, we know it as CPE 133. So all these information is what you should have taken from 133. If not, time to review it. So digital design, I define it as the act of creating a digital circuit to solve a problem. Many ways to solve problems. We're interested in digital design here, which means design a digital circuit to solve it. So the basic tenets of digital design are that they're essentially hierarchical and modular. And essentially hierarchical means boxes within boxes. The modularness is the boxes themselves. And I like to throw in there that every circuit we can possibly think of is a function of all the individual foundation modules. So I can take foundation modules, build any digital circuit. Two types of digital circuits out there. There's combinatorial circuits and sequential circuits. Now, this is known as combinatorial circuits don't have memory, sequential circuits do have memory. And that's essentially the accepted definition. And technically speaking, combinatorial circuits, the outputs are a function of the inputs. In sequential circuits, the outputs are a function of the sequence of inputs, the official definition. So the notion of digital design is based on logic operations. There are three basic logic operations, or AND operations, or operations, and a complement. I'm actually not sure if complement's a logical operation or not, but throw it in there anyway. So and, or, and complements, we actually can implement those operations such as and, or, complement with gates. So gates are a piece of hardware that implements a logic operation. So we have a whole bunch of different types of gates out there. Our basic gates are, of course, the AND and the OR, but we also have NAND and NOR, XOR, and XNOR. Now, the issue here, what we like to remember about this is the NAND gates and NOR gates are functionally complete, which means we could design any circuit in the world using just NAND gates and NOR gates. AND gates and OR gates are not functionally complete because they don't contain, you can't make a AND gate into an inverter, or same with an OR gate. But it's just interesting that you can make NAND gates and NOR gates into inverters. You can make an AND gate and perform an OR function. Of course, you can make a NAND gate perform an OR function. So in the end, the functionally complete gates are NAND and NOR. XNOR, XOR, kind of different issues here. The other issue we like to talk about is functional equivalence. And as you know, you will say there's many ways to design a circuit to solve a problem. There's not just one way. Technically, you could have practically infinite number of different circuit designs to solve a given problem. Now, some would be better than others, but the notion here is that these circuits are going to have maybe a functional equivalence, and not so much that they're equivalent circuits, but they, functionally speaking, they do the same thing. One of the important things we did in digital design was state machines. And state machines, their primary purpose were that they were circuits, digital circuits that controlled other digital circuits. So they act as controllers in circuits. There were two main types of finite state machines. One was the Mealy type, the other was the Moore type. Now, the Moore type had outputs that were a function of state only, whereas the Mealy outputs were a function of both the current state and some external inputs. These are the three accepted modules in a state machine. We have the state registers, which represent the only memory inside a state machine, and then the output decoder and the next state decoder. Just by their name, decoder, we know that these are typically combinatorial circuits. State registers are the only memory in a state machine. It's really important to realize that. The other issue here is we have to deal with setup and hold times. Now, setup and hold times are associated with clocked circuits. And the notion here is that this is our rising clock edge right here. And we're going to say that all the inputs to my circuit need to be stable both before and after this active clock edge. Now this time here is going to be the setup time, and this time here is going to be the hold time. If you change your inputs, some of the control inputs in any of these times, your circuit could go metastable, which means it's neither high or low, which makes it not digital, but essentially you don't want to do it. So this is our digital circuit. The idea here is I have a digital circuits with a bunch of inputs and a bunch of outputs. Well, that's a little bit too high level. What we want to do is kind of look a little bit in more depth at this. So a digital circuit is a circuit where you have a bunch of modules in here that are talking to each other. And by talking to each other, I mean they're exchanging data with each other, or one circuit's controlling another circuit. We didn't really specify it in this. We'll kind of get to that later. But once again, digital circuit, bunch of modules working together to produce a meaningful result. So this is our old design of a digital circuit. Essentially, we broke it into inputs and outputs, but what we want to do is move to this new model. And what we're going to do is divide the inputs into data inputs and control inputs. And the outputs are going to be, the data on the output is going to be just straight data or status output. Now the status here is going to tell something about this circuit. The control inputs is actually going to be controlling the circuit. So these are some of our foundation modules. These are actually all combinatorial circuits, and we can look at these individually. So here is a ripple carry adder. We can see it has data inputs and data outputs and data inputs, and it has one status output. This carry out's a status output. Here's a MUX. I got data inputs, I got data outputs. I'd have no status outputs, but I have a control input. Now we can say this about all of our circuits. I'd like to move up to these other more interesting circuits, which is the sequential circuits, and they're all based on registers, roughly speaking. So our favorite type of registers here are just like a simple register, but we also have counters and shift registers. So we'll go over just one of these. And so this is our just basic register. It has data coming in, it has data coming out, and it has a control signal, which controls the loading of that data. Typically speaking, on a counter, we'll have an RCO, which will be a status output, etc., etc. So what we're going to get into in this chapter here, in our new stuff here, is getting into structured memory. This happens to be a random access memory. So our new design, what we're interested in is to take this one and control it. So what's going to happen here is the state machine is going to be sending out control signals, which is going to connect to here, and it's going to that circuit in general is going to send out status signals, which is going to connect to the input of the state machine. So the state machine is reading the status of the circuit according to what those status signals are doing. It's going to change states, blah, blah, blah. But particularly, it's going to be sending out the appropriate control signals. So this is our new circuit here. It has a bunch of modules here inside that are talking to each other, but they're under control of the state machine, or I said a microcontroller. Now, in 133, we control our circuits with state machines. Essentially, what we're going to be doing in 233 is developing a microcontroller, which can also control digital circuits. So this is the foundation modules. This, I don't expect you to read this, but this is on one of the cheat sheets. It's an overview of all the modules that you should be, roughly familiar with from CPE 133. And this is our final slide, which I put everywhere, which is our RISC-V Otter module.